AI companies are competing with one another left and right by introducing their own novel patches to the same old engine. But what if the old engine itself needs to change? For nearly a decade, the world of AI has been moving faster and faster, but always along the same track. More data, more parameters, more compute. So we asked a different question. What if we change that track? At SilicoSapien, we introduced a neuromorphic symbolic transformer. Not a patch, not an optimization, but a fundamentally new engine for generative AI, designed from the ground up to overcome the core limitations of the traditional transformer. To understand how it differs, let's run a simple thought experiment. Imagine two classrooms with two teachers, each trying to teach the same lesson through two different teaching methods. In the first room, students are never taught, they are tested immediately. For every wrong answer, they are punished. The more wrong the answer, the harsher the punishment. Most students fail, badly. A few do slightly better by chance. Then they take another test, again and again and again. Over time, students don't necessarily learn the lesson, they learn how to avoid punishment. They guess patterns, they memorize shortcuts, they minimize pain by minimizing answering incorrectly. This is how traditional transformer models learn. Learning is driven by punishment minimization, effective at scale, but slow, inefficient, and opaque. Now the second room. Here the teacher explains the lesson first. Concepts are explained, relationships are built, ideas are associated. Only then does testing begin. Correct answers are rewarded, wrong answers are corrected. The result? Students learn faster, they need fewer tests, they understand the material better. This classroom mirrors how biological intelligence learns, and it mirrors how our architecture learns. The neuromorphic symbolic transformer integrates three learning mechanisms known to operate in the human brain. First, Hebbian associative learning, features that core become linked, neurons that fire together wire together. Second, neural selectivity, neurons specialize, meaning becomes localized, not smeared. And third, localized cross-entropy reinforcement, prediction surprise triggers targeted reward or correction, as opposed to global parameter reshaping. SilicoSapien is the first organization to integrate all three mechanisms inside a scalable, transformer-like, context-aware generative architecture. Despite years of effort across the industry, no prior system achieved this, because traditional transformers simply weren't built for it. This single breakthrough unlocks everything that follows. A synapse represents one feature, a neuron represents one context-dependent concept. Learning signals are localized. As a result, concepts are no longer diffused across billions of parameters. Every decision can be traced end-to-end. Biases can be inspected, failures can be corrected at the source. No need for post-hoc explanations, no longer doing approximations. Transparency is inherent to the design. This is unprecedented, the only architecture in the world that supports white-box, fully transparent generative models, aka the holy grail of AI interpretability. What interpretability researchers have been chasing for years, we built it inside this new foundation for all future generative models. Because knowledge is stored in non-diffuse local way, adhering to neural selectivity, only task-relevant compartments activate. Only relevant neurons and synapses, aka nodes and weights, load into GPU memory at a time. The entire model, aka the brain, is never required at once. The consequences are dramatic, orders of magnitude lower compute and lower energy, AI that runs where traditional transformers cannot. Traditional models have parameters with fixed size at birth. Ours grow. Neurons and synapses are created only when needed and grow with the amount of data the models feeds on. No fixed parameter count, no catastrophic forgetting, no overwriting old knowledge to learn new. We provide a small controllable set of hyperparameters, and based on these, the model flexibly scales according to the data it feeds on. All in all, this yields unprecedented data efficiency and removes the need for massive duplicated datasets. You may remember the patches from previously which AI companies and researchers introduced to the original transformer to improve generative AI models. Here's the key insight: almost all of them still work in our architecture. Data scaling, model scaling, alignment techniques, mixture of experts, chain of thought fine-tuning, KV reuse, recursive prompting, and Ingram embedding lookup. Our architecture benefits from them all. In fact, they benefit from them more than traditional transformers. Overall, this means the neuromorphic symbolic transformer can scale efficiently across all generative AI projects which are currently powered by its predecessor. This is the end of the road for the traditional transformer. AI companies and the industry as a whole has extracted nearly everything it can from the 9-year-old transformer architecture. Recent gains come from brute force, more data, more compute, more energy. And as leading researchers like Jan LeCun and Ilya Sutskever have warned, scaling alone is no longer enough. You see, every once in a while, progress doesn't come from optimizing harder, it comes from rethinking the design entirely. The car didn't win over the carriage by breeding faster horses. It won by abandoning the carriage design entirely. Our competitors are still optimizing the carriage. We left it behind. Why the others couldn't do this? Because the industry fell into a trap. When Transformers showed spectacular results around 2022, the entire industry fixated on a single metric: better generative responses. Everything else, efficiency, energy, interpretability, was treated as secondary. To understand the consequences, consider the following historical lesson. In 18th century Prussia, timber was a hot commodity for the Prussian state, so the state decided to optimize its forests for more timber yields. Natural ecosystems were replaced with neat rows of artificially planted identical trees. At first, it worked beautifully. Timber yields rose and yields prediction stabilized. Then, the forest collapsed. Pests spread, soil died, resilience vanished. What has been stripped away as inefficiency turned out to be the invisible infrastructure that made forests survive long term. This is the classical Goodhart's law. When a measure becomes the target, it ceases to be a good measure. Modern AI optimized for good generative responses and behavior, and sacrificed everything else. We took a different approach. We didn't ask how do we optimize transformers, we asked how can generative intelligence work efficiently. And there's one biological machine refined over millions of years of evolutionary pressures to be the most efficient intelligent machine known to mankind. That's the human brain. So by aligning generative AI with biological principles, we create next-generation AI models that learn faster, reason transparently, scale efficiently, and operate sustainably. This is not a patch. This is a new foundation.